Hi everyone. Today we're going to talk about elastic potential energy, which is our second type of potential energy. The first type that we talked about was gravitational potential energy. The next thing after we talk about elastic potential energy that we'll focus on are energy bar charts, and then we're going to end our video today with conservative and non-conservative forces. So let's just review from yesterday a little bit in that gravitational potential energy, remember, was very dependent on height or that vertical displacement. So we said that for our gravitational potential energy, that was symbolized as U, and then we said we also have to say U sub G to indicate that it is gravitational potential energy, because there are different types of potential energy. So our U sub G is equal to the mass times that acceleration due to gravity times that vertical displacement height, or we could substitute the H in instead, or and say Y. Okay, so the second type of potential energy that we'll talk about is elastic potential energy, and that's potential energy that's associated with a spring. So if we're thinking about Hooke's law, remember for Hooke's law, that was the force that the spring is exerting on some mass, and ultimately we know the spring force is just an interaction between some mass, like we've just seen a block with a spring. So some interaction between the block and then a spring. And we know that the force that the spring is exerting on a block, on a mass, for example, is calculated by that negative kx. And remember, that negative is just indicating that the spring force and the displacement are acting in opposite directions. We could find the work done by some external applied force on this spring block system, and we could find that by our work equals 1/2 kx final squared minus 1/2 kx initial squared. So physicists have defined an expression for the elastic potential energy to be our U sub S, so U just again representing our potential energy, and then that sub S representing that it's associated with a spring, because elastic potential energy occurs with springs. So our elastic potential energy equals 1/2 kx squared. So that would be if we're just talking about one particular instant, one particular moment in time. And we found that, again, from the previous slide, that work that is work that's done by some external applied force on the spring block system is equal to our 1/2 kx final squared minus our 1/2 kx initial squared. So it's just that elastic potential energy is where we're applying some external applied force to this spring block system, and it's not that the block is moving on its own. We're applying some force to it at some constant speed, and before we release that block and that spring system, then it's going to have some type of potential energy that we've stored into it just because we've done some amount of work on it. And we can calculate that, again, by our 1/2 kx squared. We think about the elastic potential energy as the energy stored in a deformed spring. Well, what does that mean? When we talk about a deformed spring, we just mean that we're either compressing the spring or we're stretching the spring. So a deformed spring would be any spring that isn't in its equilibrium position. So as long as it's not at our x equals 0, that equilibrium position, then we would consider it a deformed spring. An undeformed spring would just be then when it's at its equilibrium position or when x equals 0. So once we have compressed the spring enough, then we can have all of that potential energy as stored elastic potential energy. And if I release the mass, it could be converted into kinetic energy. So let's look over here at our A through D as an example. So in A, before we compress the spring at all, we have an undeformed spring where X is at 0, and I'm going to apply some external force to this block. So then that way I'm going to bring that block towards the spring to try to compress it. So let's say that I partially compress the spring with the block. So I see here that whenever I've applied some external force to the block and I'm compressing the spring, if I look at my energy bar chart here, I see that the work that's done by the hand on the spring block has increased that potential energy. So I'm increasing potential energy in terms of elastic potential energy because I'm compressing the spring. And then that potential energy that's been stored now by my spring block system is also just equivalent to the total energy. Let's say that I compress the spring as much as possible. So I have X max here. And I'm, again, holding this block steady with my applied force. And in this case, it's just the hand. Now, I'm going to get a total amount of elastic potential energy. And that's, again, just equal to the total energy. There's still no kinetic energy because this block remains steady by that external force, which is just my hand. If we go to C, let's say that now I release my hand. So I'm going to let go of that external applied force, which was my hand. But now the spring holds all of that elastic potential energy. And we know that when that spring is compressed, it wants to move back to its equilibrium position where X is equal to 0. So that spring is going to apply some of its elastic potential energy on the block. So I see that the elastic potential energy in the system is going to decrease, and it's going to be converted into kinetic energy. So I'm going to see that kinetic energy is going to increase as that potential energy is going to decrease. And I still see that my total energy of that block, a spring system, is still consistent because all I'm seeing is a change in between the kinetic and the potential. So finally, let's look at D. Let's say that the block loses complete contact with the spring because now the spring has reached its equilibrium position at X equals 0. The block still has some velocity, so it's still moving. So now all of the potential energy has converted into kinetic energy. So like we said in the previous slide, the elastic potential energy that's stored in a spring will be 0 if the spring is not deformed. So again, that just means that if we have an undeformed spring, that means that the spring is at its equilibrium position, so X is equal to 0. And remember, we said that our elastic spring potential is just equal to 1/2 kx squared. So if we're at our equilibrium position, 0, X then would be equal to 0. So then our elastic potential energy then must also be equal to 0. If we have some external work then that's being applied to some system, I could say that our work done by some external applied force is equal to the change in our elastic potential energy. Guys, we've seen that when we talked about our work kinetic energy theorem. So when we have some amount of work that's applied by an external force, then we know that that's equivalent to the change in kinetic energy. We saw that also with the gravitational potential energy. So it's no different here by us also seeing that our external applied force in terms of work can also be equivalent to the change in that elastic potential energy. So we see the same thing here. Now, the elastic potential energy is a maximum, and again, that's going to be when we've compressed the spring to its maximum ability, or if we've stretched the spring to that maximum capability of the spring. So there is kind of a cutoff or a threshold for how much elastic potential energy that we can have. We would consider elastic potential energy always to be positive, because if we square x, then of course it's always going to be positive. So in the last example, when we were talking about the elastic potential energy of this spring block system, we saw this energy bar chart. I just want to go through this again, just step by step. I know we just did it in the last one, but we will see energy bar charts pretty frequently just because it shows really shows the conservation of energy, in that we can convert energy into different forms, but ultimately the total energy of a system should remain constant. So if we're looking at our energy bar chart, which is here, we see that the vertical axis is just going to represent the amount of energy that's given of a given type in a system. So we're just going to see by how much a specific energy is represented in a system. The horizontal axis is just going to show us the different types of energy that we have in a system. So like we saw in this first part for part A, before we compress the spring, I have my hand that's on the block, but I haven't done any work on it yet because it hasn't gone through any type of displacement. And I know that the spring has not been compressed. It's still at its equilibrium position of x equals 0. That means that the spring is relaxed, the block is not moving, so I have no amount of energy here that I've done or applied to this system. Okay, but now let's say that I've taken my hand and applied some force to that block, and now I'm compressing the spring. So we saw that when the spring is just partially compressed, that the total energy of the system has now increased, and it's equivalent to the potential energy. So that means that all of this elastic potential energy that I have done by compressing the spring is just the total energy of the entire system. So in part C, let's say that now I've compressed the spring to the maximum amount possible, and the block is still going to be held steady. I've now maxed out that elastic potential energy because I can't compress the spring any further, and that's again still equivalent to the total amount of energy done by this spring block system. Now I'm going to take my hand away. I'm going to take that external applied force of my hand away from the block, and I'm just going to release the block. So once I release the block, we know that that spring was compressed at its maximum amount, so it wants to return back to its equilibrium position. It's going to restore itself to, again, x equals 0. So because of that potential energy, that elastic potential energy that we had when the spring was at its maximum compression, is now going to be converted into moving that block so the spring can go back to its equilibrium position. So now we see that our potential energy is converting into kinetic energy to move the block so the spring can reach its equilibrium position. And still, let's go back and see that the total energy has remained constant because all we're doing is converting potential energy into kinetic energy. Finally, if we look at our E, we see that the block will eventually lose contact with the spring because the spring will ultimately reach its equilibrium position at x equals 0. Once that happens, the block has just complete kinetic energy because it has some velocity. And again, our total energy was conserved because all we did was convert our potential energy into kinetic energy. All right, guys, so one of the last types of energy that we're going to talk about is called the internal energy. And internal energy is just the energy that's associated with an object's temperature. Now, let's just imagine that we have a book that we have accelerated by our hand. And we have our little physics book here. We've accelerated this book just with our hand by some outside force. And let's say that now that we've accelerated this book, it's going to slide across this surface, just this desk or table, and it's going to move towards the right, so it'll have a displacement in the right. And let's assume that this is not a frictionless surface. So if my physics book is accelerating toward the right, then the frictional force is going to be opposing that motion or that displacement, so it's going to be acting toward the left. Now, let's just suppose this time that instead of the book being our system, let's say that the surface is the system. We know friction force from the sliding book is going to do then some work on the surface. And we know that the work done on the surface is going to be positive because the force on the surface is moving towards the right because the book is sliding to the right. The displacement is to the right. So because the work and the displacement are in the same direction, then we can say that the work done on the surface is positive. But the surface isn't moving after the book has stopped. And we just said that positive work has been done on the surface. But the table or the surface hasn't moved, and there's no increase in the potential energy of the surface, so where does the energy come from? When we slide objects over a surface with friction, then we have felt, just from experience, that usually those surfaces become warmer just because of a friction. So the work that was done on the surface has now gone into warming the surface rather than increasing the surface's speed or rather than just changing the configuration of the system itself. So I did no work in terms of increasing kinetic energy or in terms of increasing the potential energy. Instead, what we've done is we've warmed the surface through friction, and that is what we call internal energy. So, I mean, if you're just sitting at your desk right now, you can rub your hand across the table and you can feel that temperature is increasing. It feels warmer. So all you're doing is giving that surface some internal energy. One of the last things of chapter 7 is talking about conservative forces versus non-conservative forces. Now, a conservative force is where we have, when we have work done by a conservative force, then we think about a conservative force being independent of the path that's taken by the particle. So the work done by a conservative force on a particle moving through any closed path is 0. And we call closed path just one in which the beginning and the ending points are the same. So that would be where our initial, we'll just say maybe we're moving in a vertical displacement. Our initial position is just equal to our final position. So if we have a closed path, we're just beginning where we end. So displacement is 0. Now, conservative forces, what's key is to remember that it's between any 2 points and it's independent of the path that's taken. A couple examples of conservative forces are gravitational force, and then also our spring force is another example. So the work done by the gravitational force on an object that moves between any 2 points near Earth's surface, it really is only going to depend on that initial y-coordinate and that final y-coordinate. It doesn't matter the distance that it's traveled between those two. All that matters is where it started and where it ended. So we can say that it's independent of the path.